So hello everyone. Okay, wait. Yeah, so hello everyone. So I will start the session now. So just introducing myself. So I am Anjali Negi. I am currently pursuing PhD in IIT Kanpur. So for today's session, I have picked up some basics of group theory. So we will start from symmetry operation first. Then group theory, we will solve one problem of it. Okay, so I will share one video now.
Everyone, in this video, hello everyone. In this video, I will be solving GATE 2014 chemistry question number 4. So this question states that the number of C2Hcs in CCl4 is. So we have to look into the symmetry of the given molecule and find out the number of symmetry elements. For example, the C2 axis, the rotation of axis C2. So first, let's look into some basic. So what is the symmetry and how you can be quantitative? So how you can be quantitative about it, like which one is more symmetric than the other, which molecule, for example, is more symmetric than the other molecule. So these questions will be answered in this video. So I will be discussing it. So the symmetry elements and the symmetry operations. So what are these? So first of all, the symmetry operation. So for symmetry operation is a movement by which any object can go from one configuration to an equivalent or identical configuration. So there is a difference between equivalent, or you can say indistinguishable, and the identical configuration. Okay, so for example, if I take the equilateral triangle, so this is the equilateral triangle, and in this triangle, let's say we denote one side as 1, 2 and 3. So if we do 1 second, so if I am rotating, okay, rotating my equilateral triangle such that this is the axis of rotation and we are doing a 120-degree rotation. So in such a way that the first that this point 1 will comes to the point where 3 third was. Okay, so this will be 1 3 2 now, and again if I am doing the same 120-degree rotation around this particular axis, so I will get 1, again my 2 will come here, so my 2 will come here, okay, and my 3 will go here, and so this will be the rotation again. But the point to be noted here is that the first configuration and the second configuration and the third configuration, all these are not particularly identical, but they are indistinguishable or they are equivalent to each other. Because what happened here is, if I am not tagging the particular side, so there will be no indistinguishability in between them, so hence they are equivalent. But if I am tagging them, you will know that they are not exactly, they are not exactly the identical like the first structure. Okay, so in the last set of rotation, if I am doing the last set of rotation, so this particular equilateral triangle I have not drawn here, so this will be similarly where my 1 from here will go to the position where it was in the starting of the rotation. Okay, so it will be 1 2 and 3. So this will be the identical one with the first configuration. Okay, so this is the example with the equilateral triangle. You can understand and apply it to any set of molecule. Okay, and so these movement by which I can get indistinguishable structures or even identical structures are called the symmetry operations. Okay, so these are the symmetry operations. Okay, now let's move into what are symmetry elements. So when you will see that the symmetry element is some entity within the body. It can be an axis, okay, it can be a point, it can be a plane. So this axis, plane or point about which a symmetry operations take place and we get an indistinguishable structure is known as the symmetry element. So we have the symmetry element and we do the symmetry operations and we find out the different indistinguishable structures or identical structures we can get, and the more number of identical or indistinguishable structures we get is equivalent to the more symmetry to in that particular molecule or structure. Okay, so example, in previous equilateral triangle example, we have seen that there was a rotational axis. Okay, so the element was axis. Okay, so if the point here is, if an object or molecule has more number of symmetry element and symmetry operations, then the object or molecule is more symmetric. Okay, so among these H2O, ammonia and the benzene molecule, you will find out that the more number of symmetry operation and element is maximum in benzene. Okay, so this you can do by yourself or it's easy. So you will find out that the more number of symmetry operation and element is maximum in the benzene molecule, and hence the benzene one is more symmetric in comparison to ammonia and water molecule. Okay, now what different symmetry element and symmetry operations that a molecule can have. So one can have 5 different symmetry element and can generate several symmetry operations from there. Okay, so the first one is the identity one. It is denoted as capital E, and I will simply tell you that it is something which we can say doing nothing or do nothing, because identity is the exactly same configuration that we had in the first or before the operation or after doing the particular operation. So for example, if I just take one example of H2O molecule and tag my hydrogen as 1 and 2, and this is my element which is axis, rotational axis, and this is, for example, if you don't know, so let's just say this will rotate at 180 degree. So what I will get is, I will get the same rotation like a flip, and so okay, so if I'm doing 180 degree, then it will be it will not be the identity. But so if I am doing the 360 degree, okay, so this will again be 1 and 2, correct? Because if I am doing 180, then this will be 2 and this will be 1. Okay, so yeah, after this, so this is something which is the same as the first configuration. So we have done only the full flip, or you can say full rotation, not even flip, full rotation. So my molecule, after doing the 360 degree rotation, comes back to the original original configuration, and that's why we have done nothing but so this is the identity, and it is found in every single symmetric molecule. Okay, or when we apply some symmetry operation, if you are doing the identity, it is always present there. So the second one is proper axis of rotation. So I will discuss this up to here only, and the other 3 I will give you the reference for that, so you can go and take the detailed notes of that. Okay, so the second one is the proper axis of rotation. So this is denoted as capital C, and in suffix there is a small n, where n is nothing but an order of operation. Now we know the symmetry element here is axis, correct? and the operation that we are doing is something which is called as rotation. Okay, so and the order of operation means n, like 2, 3, 4, 6. You will know that for if I am doing through an axis, say axis C, I am doing a 180-degree rotation of that particular molecule, then it will be n is equal to 2. Okay, and so the order of the operation is 2. For 120-degree rotation that I was doing in a particular equilateral triangle that you have seen, so there I was doing a 120-degree rotation, so my order of operation was n equal to 3. Similarly, for 90-degree and 60-degree, we have n equal to 4 and 6. So in general, the n can be calculated as 360-degree divided by the angle of rotation. So the angle of rotation is, the angle of rotation, for example, 180-degree. So 360 divided by 180, you will get n is equal to 2. Correct? Now, the principal axis of rotation is again Pn. Okay. So if you see this example, this is a square with, if I tag 1, 2, 3, 4 to the what you say, edges. Yes, then I am doing, so this is my, so if this is my particular axis, okay, and I am doing the 90-degree rotation. So you are doing a 90-degree rotation means my one will go from here to here, and I can do this 90-degree rotation up to what? Because up to 4. Okay, so n, if I am doing n is equal to up to 4, you can do and get the identity configuration. Okay, after 4 rotation. So my n will be 360 divided by angle of rotation, which will be, angle of rotation is 90. So it will be 4. So my axis of rotation, so this will be denoted as C4. Okay. So this is my principal axis, or you can say axis of rotation is C4 here. Now, again, if you will ask me what is C1, because I have not talked about n is equal to 1 order, because in n is equal to 1 order, you are doing a full rotation. So this will be n is equal to 360 by 360. So the angle of rotation is again 360. So that's why you will get the identity E. Okay. Also, you can ask what is C infinite. So if you are asking me about C infinite, so there should be something making n is equal to infinity. So if you see this particular molecule here, okay, so this particular molecule CO2 is a linear molecule, and here if I am drawing this rotational axis along these atom, carbon and 2 oxygen, you will see that if any number of rotation, I will get the same molecule, or so the order of the rotation or the symmetry element C axis has become infinite here. Okay, so this will be denoted as C infinite. Okay, and this is highly symmetric molecule. So the molecule can have more than one type of axis of rotation. So there is a point you should note that it should not be in any molecule it is not particular that it can only have C2 or C4 or C3 rotational axis, but it can have both or more than 1 and 2 axis of rotation. So for example, you can see that this is a triangular planar molecule. So in a triangular planar molecule like this, so this is, for example, let's say this is a plane, okay, and in this plane, horizontal plane, just imagine this as a horizontal plane. I have to draw this plane like this, okay, and the molecule lying on the plane horizontally, and you can see that there are 2 axes of rotation I have drawn. So one axis of rotation is here. Okay, this is the C3. Why this is C3? Because because the symmetry will be restored when my n is equal to or in order of 3. Okay, so I will be doing a 120-degree rotation. Okay, and for this particular axis going through my 2 atom, or you can say one single bond of the molecule, you will have a rotation of what 180 degree, correct? So this will be C2. Okay, to get the symmetry of the molecule again, or indistinguishable configuration, so it will be C2. Okay, now let's move to our question. So we were given with CCl4. So this is a tetrahedral molecule. So for a tetrahedral molecule, you will see that this is Cl, Cl, Cl. There are 4 Cl bond. And before I move into, so there it was asked that the number of C2 axes. Okay, so wait. Yeah, the number of C2 axes in CCl4. This was the question. So okay. So for C2 axis, my n is equal to 2, and my angle of rotation will be 180 degree. Okay, so my angle of rotation will be 180 degree. So this is my molecule, and you can, so this is tetrahedral structure. It's a little difficult to imagine. So I have drawn it in a cube, and you can now imagine that how my Cl molecules are arranged in a tetrahedral position. So this is my carbon here. Okay. Yeah, this is my carbon here, and these are the 4 Cl molecule. So for this, if I am doing the C2 operation or C2 rotational axis, so it will pass for C2. It should be doing the 180 degree rotation. Okay, so this is the one axis of rotation here. So you can say that for this, like for 180 degree, if I will rotate this, so my structure, so my structure will be such that after rotation, this Cl will be here, correct? This Cl will move here, and again this Cl will move to the position here, and this Cl to here. So this is one axis C2, I will count, and the next one is the one here. Okay, so this is again C2 doing the 180 degree rotation. So if I am rotating it like this, for example, okay, so this will move, this Cl, this will move here, okay, and this will move here, and this will come back here. So this will be the, again, indistinguishable structure for C2, and last axis is here. So you can imagine this particular axis similarly like this one, but from back to the front. I mean, from this particular phase to this particular phase, it is doing the 180 degree rotation. Okay, so this Cl will come here, and this Cl will come here, and for these two also. So in total we have 3 C2 Cs. So in total, we have seen that we have 3 C2 Cs, and so the answer is 3. So the NPTEL reference I will recommend you to go through is lecture number 2 by Professor Manabendra Chandra, Department of Chemistry, IIT Kanpur. Here is the link below. Thank you.
So if you guys have any doubt, otherwise I will move forward. Okay, so now I hope I'm audible, so I will share my screen. Okay. Okay, so all of you can see the screen, right? Yes, so so for this particular problem from GATE 2012 chemistry question number 27, this state that the symmetry operation of the four C2 axes perpendicular to the principal axis belong to the same class in the point group or groups. Okay, so we are given with four option of point groups, and in fourth option it is saying it belongs to both 4D4H and D4D. Okay, so we have to first of all I will just go through some basic of point groups, and then we will discuss what is the correct option for this particular problem. Okay. Yes, so for point group, so for point group, if you take one example, for example like this water molecule, so we have C2 axis here, and if I just write down the possible symmetry operation that I can have for this H2O molecule, then it will be identity C2 axis. So if I am saying this one to be in Z direction, so I can write it just C2Z. Sigma V, that is the vertical plane, that is the mirror plane vertical to my C2 axis. If it is in XZ, so say it is X and Z, so say this is XZ direction, so it is bisecting my oxygen and both the hydrogen, and that's why it is reflecting, so it is sigma V. And as you have seen in the previous video that there is another vertical plane that we can write it as sigma V prime, correct, as YZ, in YZ plane that it is. So these are the all possible symmetry operation which are applied to the water molecule. Okay, so yes, I will tell you what is the closed set here is. So the first property in when we are grouping all the symmetry operation is the point is the closure property. So in closure property, what we do is that if you can simply take any 2, any 3, any 4, any number of operation together, and you apply it on the molecule, same molecule, from the set that you have created. If I take for example sigma V and sigma V prime, and then I apply these operation to this molecule, so it will be equivalent to any one of the symmetry operation that belongs to that particular set, correct? So if you will apply sigma V, okay, so this sigma V is something here, and then so this will reflect so it is almost equal to identity, correct? And then the another will be sigma V prime, which will be here, and then this H will be reflected here and this will be reflected here, and that is the same operation that I can do with C2, correct? So similarly in the same manner I can combine C2 symmetry operation with sigma V, and it will give me equivalent symmetry operation as sigma V prime. Okay, so this is something which we call as the closure property, and the set that we have just write down or created is a closed set, because all the operation are coming from there only, and the combination is also equivalent to any of the operation which belong to the same set. So the combination of any given operation in the set gives symmetry operation from the set above. Okay, so that is what we call as the closure property. The second that we look into is the identity property in a point group. For example, okay, just forget about the name point group. So if I am just saying identity, it means that in the set that we have just write, there should be one identity operation that is there only. And the third one is the unique inverse. So there must be one inverse which should be unique for every operation. So for example, if you will look that when you apply C2 operation, symmetry operation, and then you again apply C2 symmetry operation, you will get the identity E. You can just look into the molecule, apply C2, so this will reflect here, है ना? Okay, and this will reflect here. And again, if you apply C2, then it will get back to the same configuration that is giving me the operation like identity. And that is you can check for every operation that you have written down in the given set. Now the last one is the associativity property that one can have from the set of operation that we have write down in the given closed set. So for example, I am operating C2, okay, symmetry operation, and then sigma v and then sigma v prime, but in a manner such that I am first operating these two and then at the end C2. That will be equivalent even if I go in a different manner where my C2 and sigma v are applied one by one and then at the end sigma v prime. So this is what we call as the associativity property that a point group can have, must have. Okay, so there are 2 points here that you can just note, that every molecule will form a group when you use all the set of symmetry operation that is possible for that molecule. So what here I am saying that if you have any molecule in your hand and you want to ask that whether it will belong to any set of point group or not, the answer is yes, it will belong to any definitely in one of the point group, because if you write down the set of operation, the whole set of operation that are applicable for that molecule, then it will definitely follow all these 4 criteria, 3 4, yeah, this is 4 criterias, and that is why it will make a point group. Okay, so while doing symmetry operation, there is certain also why the name was point group, because while you are doing symmetry operation, any like C2, sigma v prime, in the case of water molecule, you will see that there is a certain point in the whole molecule which is always unchanged, even in the inverse I, even in the identity E operation. Okay, and that is why we call it as a point group or symmetry point group or simply point group. Okay, now while selecting the point group from the given shape of the molecule that we know we have, so we go by the step, like first we determine the highest axis of rotation, second we check for the non-coincident axis of rotation, and the last one is the check for the mirror planes. Okay, yeah, so there are the categories that we can define are into 4 different steps. So these are steps. So for step number 1, you have to first look into whether your molecule belong to the special group or not. For special group, I mean that whether it is a linear molecule. If it is a linear molecule, then it must belong to either sigma C sigma V or D infinity H or C infinity V. And the second is the one where it has a multiple high order axis, that is it doesn't have any C2 axis. Okay, so so it will belong to some tetrahedral, octahedral, or I or IH kind of special groups. The second one is the if there is no proper or improper rotational axis present in the molecule. For example, it will belong to CI, C1 or CS type of point groups, where my CS is the one where all of them have identity for sure. Okay, symmetry operation present in all the molecule. Other than that, the CS have one sigma plane, and the C1 have only identity, so that is why it is C1, and Ci only I and E. Okay, in the third step, only Sn, where my n is even, exists. So you can write down the point group as S4, S6, S8, etc. Now in the fourth group, which is important to us because the problem that we have in our hand, it belongs to the step number 4, that is we have Cn axis present. Okay, and this Cn axis we have again differentiate into two, that is NC2 C2 axes which are perpendicular to Cn, or no C2 which are perpendicular to Cn. So if there are no other C2 which are perpendicular to Cn, then it will be a C type point group, where you can just go through it, like no sigma is present, no mirror plane is there. If n sigma v mirror planes are there, then it will be Cn v. Otherwise, if it is sigma h, then it is Cnh. Okay, in the similar manner, for here we have a D type point group, where my NC2 which are perpendicular to Cn can be divided into either D and H when my sigma h is, which is horizontal to the principal axis, one plane is present. If that plane is absent, then it will be another plane if present, which is sigma v. We can just write it down as sigma d, and it will belong to D and D point group. Other than that, if there is no sigma or mirror planes are present, then it will belong to the point group Dn, only Dn. Okay, now I can just simply write down the D type as so D and H, I can write it down like for Cn plus NC2 plus NCV plus n sigma v plus sigma h. Okay, and for D and D, we have to note that sigma h is absent here in this case, that is why we are going to sigma d. Okay, so Cn plus NC2 plus n sigma d. Now in the last case, where there is no mirror plane are present, then it will be Dn is equal to Cn plus NC2. Now okay, I will just write it down. So in our problem, I will again just go through the problem here. So as you can see here, that we are given that the symmetry operations of the 4 C2 axis perpendicular to the principal axis. So when we are saying that the symmetry operation of 4 C2 which are perpendicular to principal axis, so principal axis is C4 here, and they belong to the same class in the point group. So all of these C2 axes which are perpendicular to C4, which are 4 in number, they all belong to the same class in the point group. So here it is very important, like what is the meaning of class in the point group. So for that, I will recommend you to go through the lecture that I will recommend in the NPTEL course, but for the time being, I will discuss it briefly here. That a class, it is a very important concept in group theory. It provides a way to simplify the expression of all the symmetry operations in a group. Okay, so in a group, like for example D and D, we have the number of symmetry operations, and we can just simplify it by creating some class of some special symmetry operation which are actually having a combined related operation. For that is, one can combine them, combine some related operations. Okay, so some related operations, for example, in water molecule I have just shown you that if I do these two, so I am getting sigma v prime, and if I am applying sigma v prime, so I am getting C2 axis. Okay, so you can just combine some related operation and you can write it down in the class, but it's a little tricky because you have to know the character table for the D4D or other point groups, so that you can actually differentiate whether the C4 axes are grouped together in a single class or actually they are divided into 2 different or 3 different classes in a character table of that point group. Okay, so in the character table of, if you will check that in the character table for the D4D point group, you have all the C4 in the same class, and that is why we have our correct option is D4D, because there was yes, a confusion can be created between D4D and D4H point group, because if class or character table is not understandable or understood by you, then it can create little confusion between the two. So wait a minute, I will just discuss one more thing. Also, there is another definition of class, that the number of irreducible representation in a point group is equal to the number of classes of the group. Okay, so you can go through, and then if you don't understand you can ask, but for this particular problem that we have, the correct option is D4D, because because the statement here is that 4 C2 axes which are perpendicular, they all belong to the same class, and when you look into the character table of this D4D, you will find that all the 4 C2 belong in the same class. Okay, for this I will recommend you to go through this NPTEL reference, Chemical Applications of Symmetry and Group Theory by Professor Manbendra Chandra, Department of Chemistry, IIT Kanpur. So here is the link below. Thank you. Okay. So I hope it's clear.
Yes, ma'am.
Okay. So I have another. What is this? Okay. Okay, another problem I will be sharing now. everyone. In this video, I will be solving GATE 2017 chemistry question number 10. This question states that the complex vanadium oxide, chromium oxide, and manganese oxide ion exhibit intense ligand to metal charge transfer transition. The wavelength of this transition follows the order. So we are given that these exhibit ligand to metal charge transfer, and we have to find out the order of the wavelength of the transition. So before that, let's move into some basic. So the charge transfer transition denoted as CT. So the question is that why is it that some transition metal complex are intensely colored in solution but possesses no d electron. So we know that there is a possibility of dd transition and it shows color in the complex. So if there is no electron in the d orbital of the metal, then how what is the reason for the color, intense color for a metal complex? For example, KMnO4, where manganese has oxidation of +7 and with the electronic configuration of 3d0, so there is no electron in the d orbital. So it declined the fact of dd transition happening here. But instead of that, it still shows a intense color, KMnO4, like purple. So there are things that we have to note here, that the vacant metal d orbital is a very good acceptor here and can accept the electronic charge density from the ligand system or any oxide system, correct? Because there is because my d orbital is empty here. In transition metal complexes, change in electron distribution between the metal and a ligand give rise to the charge transfer CT bands. Okay, and this CT absorption these lie in the UV regions and are intense and they where the selection rules are actually allowed. So these have epsilon value of up to 50,000 or greater. Okay. Yeah, but in the case of where only dd transition is happening, we see that the delta E is very small for the transition to take place. So when the delta E is very small, the epsilon max value is also very less than or equal to less than 20 liter. Uh, This is also less than 20 liter molar inverse centimeter inverse. So this gives me the points where for good detection, I should actually take a very high concentration solution for this with or even a higher path length of the cell. Also, this DD transition shows a very less intense color because of the selection rule forbidden DD transition. This result in a weak absorption. However, in the case of the CT transition, we detect it is very detectable in a low concentration of the analyte also, uh, following the law of Beers-Lambert law, where absorbance is equal to silent, B is the path length, which is generally 1 centimeter, and C is the concentration. So in the case of CT transition, it is possible to detect even the low concentration because of the epsilon value, which is Emax, is
very high, that is up to 35,000. So the charge transfer transition, particularly for the LMCT, if we talk about, it is from the metal line, and it is in between the metal line orbitals and the ligand orbitals. So the metal ion, when it is in highly oxidizing state and my ligand is in reducing state, then this case will be referred to as ligand to metal charge transfer. And the example for that, as we have discussed, KMnO4, where my O2 negative is highly reducible, and the intensity of the color is due to the fact that there is a high probability of these transition taking place. And the example are mercury I2, which is brick red in color, and CrO4 2 negative, which is yellow in color. And the charge transfer transition, the CT transition, are actually classified into metal to ligand charge transfer, so MLCT, or ligand to metal charge transfer, or LMCT. There are other two categories also where there is two oxidation state of metal is present. So it will be a metal to metal orbital, and if there is state of ligand is present, then it will be a ligand to ligand. But here we will focus on the LMCT first. So the ligand have actually the sigma antibonding, pi antibonding type of orbital, also non-bonding orbital, molecular orbital. So if the ligand molecular orbital are full, so the charge transfer may occur. So the charge transfer may occur from the ligand molecular orbital to the empty or partially filled metal d orbital. And for some example I have given here. So for LMCT, very common for coordination compound having pi acceptor ligands. So these are the example of pi acceptor ligands. So in terms of molecular orbital, let's look into. So this is a D6 uncoordinated metal. So D6, okay, and here we have a ligand where it's a sigma orbital, for example. So this is a full sigma orbital. So in octahedral complex, my molecular orbital of the given complex will look like this, where the splitting of degenerate d orbital take place as in octahedral field, following with splitting in T2G and EG orbitals respectively, and then the charge transfer LMCT will take place from sigma orbital here to the one which is empty. So it will be something we can, this is sigma antibonding for it. Okay, so this will take place from the full ligand orbital to the empty metal orbital. So this is the LMCT, and so this will be the energy or the wavelength associated with it will be observed as in the absorption band. Here you can look into this figure where this T2G and EG comes from the metal, okay, and my EG acts as a sigma antibonding here. Also, the transition that I have shown here is from the sigma. It can actually take place from either sigma or pi to the antibonding of sigma antibonding or pi antibonding. So, for example, here, transition can take place even from the full pi orbital or full pi antibonding to the EG sigma antibonding, correct? So coming to our question, which was asked that these given complexes, we should find out the order of the wavelength of the transition for the LMCT. So for LMCT, so we have to find the wavelength of the given transition. So before that, we have to note that as the Z effective increases, so Z effective is the charge between on my metal orbital, so it is a nuclear charge. So as it increases, it will attract more the ligand orbital, correct? And so my energy order will be, so ligand will act as a donor and my metal will act as a acceptor. So so the oxidation state is as follows: so vanadium plus 5, chromium plus 6, manganese plus 7. So you can see that the molecular orbital will look like something for the Mn. So this is, if it is my Mn plus 7, so my ligand is here, okay. And for chromium, it will be a little higher. And for vanadium, so overall, the transition from ligand to metal, the energy order will be, so the energy order will be highest in vanadium, and then chromium, and then manganese. So this will be, the energy order is, okay. And as we know, my energy is inversely proportional to wavelength, so the order get reversed in the case of wavelength. So my wavelength order will be this. So the correct option for the given question is option number C. Okay, and I will refer you to go through the lecture Charge Transfer by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link is attached. Thank you.
So if you guys have any doubt, you can ask. Is it clear?
Yes, ma'am.
Okay. So the dates are out.
Ma'am, I have not checked.
Okay.
I think today was the date of admit card, no?
Okay. I think where is the dates? I think are out already. 4, 5, 11, 12 of February. Admit card will be available today. So okay, we will meet in the next live session. So keep preparing. All the best.
Okay, ma'am. Thank you.
Okay, 9 January admit card. Okay, Gunasli. Yeah, thank you. Thank you so much for joining. Thank you, Afrin.
Thank you, ma'am.